Okay, so what we want to do now is we want to interpret the magnitude of the equilibrium constant and see what it tells us about the reaction. So in my simple example, I have reactants over here on the left, and we have an equilibrium established with our product. So at equilibrium, and we remember that we compute the equilibrium constant K by taking the products and dividing them by the reactant concentration. So if I have an equilibrium constant K that's very large, 10 to the fifth, that's 100,000. That tells me I have 100,000 times more products than I do reactants. It means that the reaction, when it goes, it heavily favored my product side of the reaction. It means I have very few reactants left at equilibrium, and I have a whole lot of products. So this would definitely be a product-favored reaction. In fact, any equilibrium constant that's greater than 1 will indicate that it's a product-favored reaction. The larger the equilibrium constant K is, tells you how much products are favored at equilibrium. If K is nearly equal to 1, that's just a good mixture of reactants and products. If it's a little less than 1, it's going to be reactant favored, but only by a little bit. If it's just a little greater than 1, it's going to be a product favored reaction, but only by a little bit. Okay? If K is very small, that means we have a reactant-favored reaction. And how would that happen? So if K is equal to products over reactants, and this value is really small, 10 to the minus 3, 10 to the minus 4, 0.000015, something in that neighborhood, you know that you're going to have a very large concentration of your reactants and a very small concentration of your products. And the reason that that's the case is because that's the only ratio that will produce a very small equilibrium constant K. So to sum this up, large equilibrium constants, very much product favored, okay, product favored. If the equilibrium constant is close to 1, you have a good mix of reactants and products. They have a good mix, reactants and products. Just remember that if it's a little over 1, it's still a good mix, but it's slightly product favored. If it's just a tiny bit less than 1, it's still a good mix, but it's reactant favored. And if K is very small, then you have a reactant favored reaction. Okay, because that's the only thing in this equilibrium constant expression that can produce a really small K is you have a reactant favored reaction. Your numerator, your products, is very small and your reactant concentration is large. Okay. So interpreting the magnitude of an equilibrium constant examples. So here I have 3.3 times 10 to the 81. That's a huge equilibrium constant expression. I'm sorry, a huge equilibrium constant. I mean, this is phenomenally huge. I'm not even sure that that's quite real. It's so huge. That means that the reaction has gone all the way, effectively all the way to products. So it's made water, and that you have probably an unmeasurable amount of hydrogen and oxygen at equilibrium once this reaction gets to equilibrium. And so just remember your K is calculated. In this case, it would be H2O second power. And then down here you would have H2, that would be to the second power, and then O2, that's just to the first power. And when we calculated that, you came out with 3.3 times 10 to the 81. There's no units on an equilibrium constant. Okay, that should make you happy. And all this means is that the reaction has just gone essentially all the way to products, and you have an unmeasurable amount of reactants that are left. So quiz, a mixture of O2 and ozone are placed in a sealed container. After some time, only the O2 can be detected. What's a likely equilibrium constant for this reaction? Well, here's your product, which is O2. So these are your products, okay? It's just the O2. And so you allow the reaction to go to equilibrium, and when you try to measure the concentration of ozone, that's this stuff over here, this is your reactant, okay? And O2, the only thing you can detect are products. And remember, this would be concentration of O2 to the third power and divided by O3 to the second power. So products over reactants. And I can't detect any of my reactant. All I can detect is product. Means this number is large. Not just large, it's huge. And this number is so small that I can't detect it, okay? So small, can't detect. Just think of it as a really small number, okay? So what's likely to be your equilibrium constant for the reaction? Hopefully you get it. All right, let's look very quickly at the effect of altering a chemical reaction on K. So let's start with this. You've got a chemical equation, remains balanced, and we're going to just go ahead and make sure that you understand that this is an equilibrium reaction. What happens if we take that equilibrium mixture and we multiply everything, all these coefficients, we multiply or we divide by some constant. In this case, we just multiplied everything by 2. If you multiply this by 2, you multiply this by 2, you multiply this by 2. I could have also divided by 2. All right. What happens if the reaction is reversed? Okay, so let's say instead of the forward direction, A plus B goes to C, we reverse the reaction. Now, what we're saying is that we have an equilibrium constant. We've got some kind of an equilibrium constant for this reaction, and now we're manipulating that reaction by, in this case, multiplying all the coefficients by 2. In this case, we're reversing the reaction. What happens to the K value? So we'll have a new K value here. We'll have a new K value here. And if we know the original K and we can track what we do to the reaction, we can compute those new K values without doing a whole lot of work. What if we take another chemical equation and we add it to the original chemical equation? Well, if we do that, we're going to get a new K value, and we can make that determination based on the old K value. All right? So there's our new equation for which we'll have a new K value. All right, so in the first place, let's do the easy one. The equilibrium constant of a reaction is reversed. So here is our original reaction. A plus 3B goes to 2C. Now, I plucked 5 out of thin air. I made it up. All right, so don't make a big deal out of the 5 here. It was just an easy number for me to work with. All right, and you'll see why in just a second. So the K value, K1 for this reaction is 5, and I arbitrarily picked it. Now, here's what we did. We reversed the reaction. So all I did was I took 2C and I made it the reactant, and I made A and 3B the products in this subsequent reaction. So can we tell what K2, the equilibrium constant for the second reaction, is if we know what K1 is? And the answer is yes. Here's why. Let's look at the equilibrium constant expression for this reaction, for the first reaction. It's C squared over A times B cubed. And that's because these are the reactants, okay? These are the reactants. Okay, these are the products. All right. Now, all I'm going to do now is I'm going to do the equilibrium constant expression for the second reaction, and here it is. Now, what were my reactants are now my products, A times B cubed divided by C squared. What was my product is now my reactant. And that is simply the inverse of the original equilibrium constant expression. And if it's the inverse of the equilibrium constant expression, then all you have to do is take the inverse of the original equilibrium constant. And that's what we did here. We've got 1 over 5, which is just 0.20. So K sub 2 in this case is going to equal 0.20. Okay? So if you reverse a reaction, all you do is you take the inverse. Take inverse of the original, the equilibrium constant, which I'm just going to kind of abbreviate here because I'm running out of room. Take the inverse of the equilibrium constant for the forward reaction. All right? All right, when a reaction is reversed, the new equilibrium constant is simply the inverse of the original equilibrium constant. Let's change the coefficients. Okay? So in changing the coefficients, again, I picked 5. Okay, this is my original equilibrium constant for K1. That's for this reaction right here. All I've done is I've gone through and this is the equilibrium constant expression for this reaction right here, the reaction number 1. Now what I'm doing now is I'm multiplying all the reactants and all the products by a factor of 2. So all I've done here is I've multiplied everything in here by 2. Now let's take a look at the new equilibrium constant expression. My K sub 2 is simply product C to the 4th power divided by reactant A to the 2nd power and reactant B to the 6th power, just using the coefficients as the exponents. Well, how could I get to that if, with respect to the original equilibrium constant expression? Is there a simple way to do that? The answer is absolutely. If I have a multiplier, whatever that multiplier is, and that multiplier is 2 here, all I need to do is square each of the exponents in the original equilibrium constant expression, and that's going to give me my new equilibrium constant. In this case, it's going to be 5 squared, which you guys know is 25. So think about it this way. 2 times 2 is equal to 4. 2 times 3 is equal to 6. And 2 times 1 is equal to 2. All right, so that's all you have to do. So if you have a multiplier, when the entire equation is multiplied by a factor, the equilibrium constant for the new reaction is raised to the power of that factor. Okay, so all we did was the original equilibrium constant was 5. We squared it because our multiplier was 2, and that gave us 25. All right, if our multiplier had been 3, if I had multiplied each one of these by 3, I would have simply cubed the original equilibrium constant, and that would have given me my new equilibrium constant. Okay, that's all you have to do. Sum of reactions. This is the Hess's law of equilibrium. You remember from first semester with Hess's law that you had to add reactions. And if you had the same component on opposite sides of one reaction and another reaction, you could cancel it. And if you had, if they were on the same side, you simply added them up. All right. In this case, here is my reaction 1, and I've established that the equilibrium constant is 3 for this reaction. And my reaction 2, 2C plus B produces 2D. That equilibrium constant, I'm calling K sub 2, that's 4. So I have a K that's equal to 3 here and a K that's equal to 4 here. These are just my arbitrary equilibrium constants. Now what I'm doing is I'm adding these reactions up, and I think you can see using the technology from Hess's law that the 2C is on the product side of the first reaction and 2C is on the reactant side of the second reaction, and so I'm going to be able to cancel those two C's. And there's nothing else that I can cancel. I've got a B here and a B here, so that's going to be two B's. And I've got an A. There's no A's over here on the other reaction, so that just gives me A. And then I've got two D's. What we're looking for is what is this equilibrium constant. All right, so here's how you can get it rather easily, since you already know the equilibrium constant for the first two reactions. Let's take a look at the equilibrium constant expression for all three reactions. So here we have the first reaction. So this is the equilibrium constant expression for reaction 1, C squared divided by A times B. Okay, and we've said that's 3. K2, that's the equilibrium constant for that reaction. And so we've got D squared divided by C squared times B. And then for the third reaction, that's going to be this guy right here. So we have D squared divided by A times B squared. Okay, so now that we've got all that, let's just take a look at what happens mathematically when we do something like sum those two reactions we get. And this is presuming we haven't canceled yet. We're about to. A plus 2B plus 2C will produce 2C plus 2D. We can cancel the two C's. We either cancel them up here before we add them, or we cancel them down here. All right, so, but let's go ahead and let's add everything up. Looks like I haven't canceled the two C's yet. So if I do the entire thing, okay, this is going to be C squared plus D squared, so that's C squared times D squared. There's your C squared, D squared. And then down here in the denominator, you've got A times B squared times the C squared. And what you're doing really is you're simply multiplying this equation times this equation. That's all you're doing. So you are multiplying those two equations. Now, you've seen that I've tried to cancel those two C's 2 times, and finally I'm going to get to do it here. The two C squareds go. So whether you cancel them up here, you cancel them down here. But for the purposes of seeing what's happening, we're going to do this. Now, what you get when you do that is you've got D squared over A times B, which gives you your B squared, and that winds up being this equilibrium constant expression. Multiplying these two equilibrium constant expressions gives you this equilibrium constant expression, which was the original equilibrium constant expression that you got from simply adding those two reactions. All right, so if you get two reactions that you add together, all you'd have to do is multiply the equilibrium constants, and you get the equilibrium constant for the product of those two reactions, or the sum of those two reactions. Okay? So just multiply the original equilibrium constants. Summary: multiplying a reaction by a constant will raise the equilibrium constant to the power of that constant. When a reaction is the sum of the other reactions, the equilibrium constant for the new reaction is the product of the equilibrium constants for the component reactions. So I'll just give you a quick hint here. If the equilibrium constant for the reaction is this and is equal to K, what is the equilibrium constant for this? Well, this just looks like the reverse. So we've talked about what to do with that, okay? And you can answer that in class. And then here is a harder one. Given the equilibrium reactions, here's reaction A, X produces Z, and we're just saying arbitrarily that the K value for that reaction is A. And then we're going to have reaction B, which is Y produces Z, and that gives us a K value of B. Now, what we want to do, and remember when you did Hess's law, sometimes you had to manipulate reactions to get them to add appropriately. This is the sum of these two reactions that we want. Now, you may have to manipulate. What does manipulate mean? Well, you might have to reverse a reaction. You might have to multiply by reaction. I'm not going to tell you precisely what to do. But once you get a sum, what you're ultimately going to do is you're going to multiply, you're going to manipulate it, get the appropriate equilibrium constant, and then you have to multiply. All right? Remember, your goal reaction, this is your goal reaction, is that guy right there. Okay, that is a long video. I apologize for that. Let's stop.